watching you. So let's start this second talk today with Milliam Vickery, which is going to speak about parabolic Anderson model with colored noise on the torus. So please.
Thank you, everyone. Uh, Happy birthday to Volker. This has been a phenomenal conference over the past week or so, getting to know everyone. I just met Miguel in China. We met in Beijing. He gave a talk about quantum physics and the new perspective of the quantum jumps, and it was quite fascinating. We went hiking together on the Great Wall of China, and we got to know each other. We got to talking, and I'm really honored to be here. Glad to be here. It's wonderful to get to know this community. Everyone's really nice and thoughtful, and I'm not an expert in math physics, but I hope that introducing some of these topics from my thesis research, which are now published in a paper in Bernoulli, will be of interest to the people who have assembled here. So to start, the topic of our presentation today is the stochastic heat equation. And what makes it different from the heat equation is that there is a feedback term here. So our methods actually make it possible to replace this lambda with a Lipschitz function. But the presentation is greatly simplified because all of the methods work essentially from the linear case. If you have a function here, you can just replace it with the Lipschitz norm and work over the upper and lower bounds of the function's Lipschitz norm. So it essentially reduces to this linear case. And what we're introducing here is this noise here that's going to be a Gaussian random variable. And when you have this noise term here, it's going to give constructive feedback to you. So if this is the deterministic solution to the heat equation, here is time. This is t equals 0 here. And you're going to have sort of a slow and steady spreading over the torus, which is equivalent to an interval in R. But if you add a little bit of noise, you kind of get what you might expect, which is that a little bit of a noisier curve. That's almost the same as the solution. For this deterministic case, this is lambda equals 0.1. But once you add a larger magnitude of noise, such as lambda equals 2, then what you get is a very high peaks that are isolated. So the peaks are interrupted by valleys, and this is a little bit on a fractal scale. So this feedback can become very strong. If you look here, this is something like 1.5 times 10 to the 19. So it's a pretty interesting mathematical object to study. And there will be less today about this topic of intermittency. We'll get to it a little bit at the end. But the new innovation is that when you're in R, when you, this is for white noise here, and so we are introducing a new type of noise, which is strictly less irregular and less oscillatory than white noise, which we're calling the colored noise. So a little, yes, please go ahead. Yes. Well, there's a feedback term here. So I don't think you would have a conservation of something like the L1 norm in the case with feedback. That's a very interesting question. Let's try to look more closely at the quantities which are conserved. We have our result is that the norms, the moments, we calculate the LP moments of the solution, and they grow exponentially, is what we proved. So that would not be conserved. That would be you can conserve the growth constants, but they go to infinity, and that's one of our results. So when you in order to integrate a random variable, this is how you would approach it for a martingale. You look at a functions sort of to define this kind of you take these functions which have a value at time ti. So this is something, this xi has to be in the sigma field for time less than ti. And interestingly, unlike the case where the sigma fields are these algebras are getting smaller with time, for sigma fields for a random process, they get bigger with time, which is sort of an interesting uh, fact that would be interesting to reconcile for some future work. So what you do is that you have a function that has a set value at the beginning of the interval, and then that function kind of controls the process on this short time interval. Then you replace this one, this increment with the increment of the random process. So it's going to be weighted by xi between ti and ti plus 1. And this jump, if you integrated this function as a Lebesgue integral, it would just be xi times ti plus 1 minus ti, right? But now there's sort of a random value from this martingale for the increment. And this is the Ito integral. It may or may not be familiar. I'm sure you've heard the name before. Basically, we prove these types of functions are dense, and then we get for these are going to be dense in L2, and then you can sort of define this Ito function, this Ito integral on L2, and the properties that you get from these simplified functions that you prove different identities, and they hold in the limit because of this L2 norm. So this is how you define the this is how you define the stochastic differential equation. It has different weightings for the stochastic part and the deterministic part. This is the drift, and this is the stochastic part. And we define it implicitly. So you have this equation holds. We say x is the solution if this equation holds. So what we do in the PDE context now is, instead of having MT be a increment, it's going to be a measure. So you're going to measure a set A with a random function that's indexed by time. And and so for an example of this would be if you wanted to have white noise on a set in RD, this you could make it a Gaussian random variable, and then you're going to make the covariance equal to the Lebesgue measure. So this is going to give you white noise if you have a process that's on a question. Okay, if you have a process that is a random measure, you put in a set, and it's going to give you out a number as a Gaussian random variable, and then the covariance is going to be the measure of the set. And we can define the simple processes. It's going to be now a time interval and an indicator function for a set. And we're going to define the integral on these things here. And what you get is you get this weighting function. Now that's going to multiply the measure is going to be taken over B intersect A. So we're putting in B here, and this is measuring B. And now it's going to yeah, this is integrating over a set B, and we're going to take the intersect of B and A, where A is this indicator function, and we're going to multiply times the number it gives you for the time increment and the set. So we define the solution implicitly again. It's going to be it has to satisfy this implicit equation. U is going to go here into the uh, equation, and this is going to give, we're basically going to do Picard iterations and control the growth of them in a minute. So we have something like the Ito isometry. We call it the Ito-Walsh isometry. And this is that if you take the expectation of this product, we can move that expectation inside the integral, and we can have this function, which is called the correlation of the noise. So this noise correlation is kind of the key of our innovation. So if this was white noise, the noise correlation would be the it would be the Lebesgue measure of a set, right? So if phi and psi, now they're going to be an L2 of TD. So if these were indicator functions, then it would just be the Lebesgue measure of that set. So it would just be the L2 norm of those two functions. Integrate the L2 norm. And the Plancherel identity would give us that would be, if we write these Fourier series, for Plancherel, it would be AZ B0 plus the sum of AK BK bar for white noise, if we wanted to just take the L2 inner product of those two functions. But what we're going to do is we're going to divide by K over 2 alpha, and that's going to give us the sort of mollified white noise, what we call the colored noise. And this is the heat kernel on the torus. So you have to take the heat kernel on R, and then you have to add all, so that if you look at the torus as R mod 2 pi z, then you have to add, if you want to have the heat kernel on the torus, you have to add back all of the values of the R, the real heat kernel, on the equivalence class points. So this gives us then the heat kernel on the torus, and you have this nice property that you can transform from integrals over the torus back to integrals over R by including this sum, and we take the product of coordinate wise. So that's very nice because we have the exponential here, so it's possible to do that. This is how it looks like. So it starts out as a delta function. It starts very, very skinny and tall, and then it goes to be a constant number. So we're going to have to do two things to show that our equation has a solution, to control the Picard iterations. We have to control them in this regime here when it's more similar to a delta function, and then it's much easier to control them in this this higher time regime. So this is how we represent the correlation of the noise. That this this gamma, this is sort of almost a gamma function, and it's constructed to give us the Fourier coefficients that follow that we prescribed here, which is this. This is what we wanted to have for the Fourier coefficients. So we'll just go quickly through some of the properties of the noise here. So this is the formula here. This is the inner product now. This inner product from the noise correlation, we can write it as a integral now with F alpha rho in the middle. It's going to integrate to 0 is one of the nice properties that we have with this thing. And then that means that if we have rho equals 0, this is going to assume both positive and negative values, which is going to give us a more difficult time with the analysis. So what we add is we add on this term here, rho over 2 pi d. And then that is going to make it so that if we take rho to be large enough, then this F alpha rho will be non-negative. And that is there's a constant theta where we can show that this gap is bounded here. And this is the Fourier coefficients we mentioned earlier. This is the construction of the noise. So if you have alpha equals 0, then you're just going to have a coefficient 1 for all of the elements. So this is how we write the mild solution here. And this is now indicating against the noise as a random variable, not as a correlation. Then we introduce the Ito-Walsh isometry we mentioned. That, just to remind you of it, I added it again. So we're gonna this kind of thing here, you can see that it's something like a convolution. It's not exactly a convolution. So my collaborator Le Chen, for his thesis research, he invented this operator delta to describe the kind of convolutional identity. And so this is related to starting at S, right? As you start at S, and then you go for seconds S, and then you start at T minus S, and then you go up to T. That's kind of how I see it. And then this is starting at X0 and passing through Z, and then going from Z to X. And it's kind of like splitting up a process into two kind of legs there. Yes. So the goal here is that this term here, we're gonna plug it back into the equation. We're gonna substitute again, and then it's going to give us this term is going to be, instead of this E bar, this blackboard E, now it's going to be a term that involves Gaussians. And then the blackboard E is going to be kicked up to a higher order term that involves lambda to the fourth. Yeah, it's the Picard iterations. The what is the might solution? Yeah, the might solution. To compute the mild solution directly is not possible with the stochastic noise. If so, in the field which is known as regularity structures or paracontrolled calculus, what they do is they break down the mild solution into a number of terms that they have some good techniques for controlling. And so that's the ongoing research right now. That's what I'm working on right now. No, here's no randomness. This is something like the Ito isometry. So we're gonna just control the norm. So this is the idea here, is that we have this delta operator for my advisor. Then we're gonna write a series math cal ln, and it's gonna be each of these convolutions put together, and then this here is going to be the initial condition, and then we're going to write this expectation value as a sum of this series with this lambda 2k here. And we're going to show that this is a like a Taylor series for exponential. This is something like x is going to be something like lambda to the 2k over n factorial, and it's going to converge. So these are the examples of ln. So this is sort of like you start at S. Question. This previous slide. Okay. You can reconstruct all of the moments of you so that there's you can prove that the Pth moment is bounded. It's equivalent to the L2 moment. If you calculate the L2 moments, then and you show the L2 moments are bounded above, you can show that all of the LP moments are bounded above. And it's in terms of T. What's going to be moving forward is T. So that's sort of the uh, that's the reason why we're only doing the L2 moment. I mean, since U is a random variable, you're not going to get like an explicit formula for U. I don't think anyone does that, as far as I know. That to take a random variable and sort of create an explicit formula in terms of simpler random variables. It's Yeah, that would be pretty interesting. I mean, there's some new results about that of doing stochastic Taylor series, and I think that it would be something that would be worth working on because I think it's better to have the explicit kind of formula. So yes, something like a Taylor series or another series, a Fourier series, decompose it into subspaces. These are all really interesting directions to go in. But I don't know if yeah, for the also, looking, yeah, this would be an interesting direction, as you mentioned. So this, as I was kind of saying, the idea is that you can kind of look at this like a pin Brownian motion, which we're going to get to in a minute, because it's like you're starting here at x0, you're going to z, and then you're going from z to x. So it's sort of like this gives you a probability distribution in going from x0 to some point in s seconds. And then we're looking at the other t minus s seconds. And then we're going from, it's sort of like starting at s and going to t. Where can I get to from z if I know I'm going to end up at x? And this is what we were talking about, the pin Brownian motion. This is, you divide by this term here, which is one Gaussian, and you sort of look at, if you have two Gaussians, how do you go, if you start at x0 and you end at x, where might you be in between at time s? So if we put this pin Gaussian instead of the single heat kernel, now we've kind of combined two steps into one, and we can look at this, take this Gaussian outside, and this is going to help us go to be less stochastic, less random, getting more precision and control over the LP moments. So the LP moments are something that some of the authors in the field, Carmona and Molchanov, are famous authors who worked in the discrete parabolic Anderson model, which is on ZD. Uh, so yeah, we're gonna show now that yeah, and then my advisor and Le Chen worked on uh the RN case, or actually R1, because there's no solution known for R2. R2 requires this advanced calculus, para-controlled calculus, and then higher order terms, there's no solution. I think so. This is what we're going to prove. We're gonna turn these pin Brownian motions into a constant times t to the n over n factorial. And there's an older condition called DeLange's condition. And in this case, this is why for alpha equals 1, uh, alpha equals 0 is white noise. So 2 times 2 greater than d, you don't get this Walsh integral working. And it actually, for d equals 2, it's pretty complicated to get it to work. But the Walsh integral doesn't work. You have to use these new methods. So in our case, we're going to recover the same condition that DeLange had for white noise and DeLange's condition is going to be sort of like tight. Our condition on our noise is going to be the same as what DeLange's condition would have been. So we're keeping in mind the heat kernel here. So we're gonna have to work for small time. This function hn, it's gonna give us sort of a control on our norm. K1 is going to be for small time, K2 is going to be for large time. And then it's going to be a convolutional function, but we can show that the convolution is less than t to the n over n factorial. We can show there that you can you can compare them. So the case for large t, uh, we showed that these Gaussians are equivalent because you can you can just treat the Gaussian with the larger time as a constant because the Gaussian gets closer to being a constant as time gets bigger. So we can compare the pin Brownian motion to just a one single heat kernel because S is going to be the smaller one. We can, and then if when T minus S is a smaller one, it's the same situation. So we just have to pay attention to one. So in this case, we've replaced now the pin Brownian motion with a kernel. And now convoluting with this noise just gives us back our inner product from before. And we showed that if we increase rho, if we before this function was positive and negative, but now it's we've increased rho to so that it has a lower bound, and that means that this thing is going to be positive now. So and you can evaluate it using this Plancherel. And this is after the calculation. So we can, if we integrate this thing here, it should give us, it's just going to be dividing by k to the squared, and we're going to get that condition we had before. So this is k1 of s from here, and then we're going to be integrating k1 of s, and it's going to give us back that delaying condition we showed before. So this time here, now we want to have it be small t, right? And we're going to need to use two pin Brownian motions on R. So we're going to come, so because because this is so tall and skinny, this is like almost the same situation as R. And my Lechen, the thesis committee member, he already proved the situation on R. So, but we have to be careful because you can have a situation on the torus. If you remember, we're going to be nesting these G-bar pin Brownian motions over and over. So you can't control the base point. You can't assume the base point. So if you have a situation where the terminal point is close to this kind of branch cut on the torus, you could have a situation where there's actually a pretty high positive possibility that Z is going, Z here is very, very far from X. So on R, this would be a very low probability, but actually you're approaching this branch cut and there's sort of a probability mass that accumulates here. So you could have a situation where you actually have a positive probability that's not bounded by the R. And it corresponds to a situation like this. This is where you're centered at 0, right? But if you have a Gaussian that's kind of off center, you could sort of move away from the main hump of the Gaussian, and you could move towards the branch cut in the opposite direction, and you could end up back sort of under the probability mass of the Gaussian. So for this reason, we have to look at the mirror point of X and include that in the bound here on the Gaussian on the torus. So that all being said, now we are in a position to evaluate some terms like this, where X star now it's going to be either X or its mirror point that we showed before. And we have to think also that the noise itself, this F alpha, it has one singularity on the torus, but when you go back to work on R from working on the torus, that singularity is going to be an equivalence class. So you could have some kind of rapid growth of the f alpha function close to the image of negative pi or pi, even though you even though on the torus it just has one singularity. So what we want to do then is we're gonna just use x to the negative d plus 2 alpha, and this is an upper bound on our noise. That's defined on RD. But we have to, like as we mentioned, this pi star now that represents the different images of the singularity that would be present on RD after the fact. So this is a formula that is pretty classical from the theory of the pin-Brownian motion, and it's going to make it possible for us to evaluate these integrals. So now we're working over RD, and this is the Fourier transform of the correlation. This is going to be from our noise right here, and this we're gonna be showing that this once we've worked over the Fourier mode here for the dimension one, this function here is going to be an upper bound on those terms we were just looking at. And so this when you evaluate it out, we can make a substitution here to ignore this piece here and replace it with the S. Then this is K2 of S now. That's going to be in our upper bound. So this is the calculation that we perform, and it's basically the most important thing is we're integrating against S here, integrating against the time variable. So this is going to put the 2 alpha plus 2 in the denominator, and this is going to reproduce DeLange's condition, which is the result on RD for color noise. Then so we've now achieved this bound with HN, and that will give us what we were looking for. This gives us the bounds on the pth moment. So this bound on ln is that we showed that this is going to be less than or equal to the convolution. So it's going to be sub exponential growth in t. So that gives us the existence that we wanted, and the mild solution is always going to be unique. So now there's an interesting question of the work that we did on the lower bounds for ln. So this is the definition of intermittency that comes from the publications of Carmona and Molchanov, who studied this problem on a lattice. They found that that this was a useful term for quantifying when you get these kind of isolated high probability island, these isolated high magnitude low probability islands. So it's the idea is you're having events that are improbable and isolated. So this is because this function is convex. If you get it for p, you can sort of, if you get it for p equals 2, you can interpolate for the other values of p. And the idea is that you would want to show that these things are different. So showing that there's that you have a lower bound on this thing is going to give you the result that these are non-equal. Because I think well, let me not do too much improvising, but I think that one should be 0 and one should be non-zero. So our first attempt to demonstrate to make a lower bound was that f alpha rho is non-negative. So let's assume that rho is large enough. So that's sort of a proof of concept kind of thing. But if you assume that rho is bigger than this lower bound, if rho is positive, then the techniques that we just did, we also had lower bounds on the pin Brownian motion, and the lower bounds were will give you the same behavior that we can that we produce the lower bounds from the other slides. The upper bound, there's an equivalent lower bound from what we already proved. So that was less satisfying because we wanted to work with the we wanted to work with rho equals 0. The goal is to get to rho equals 0. For the upper bound, we can just take a bigger rho and get an upper bound. But for the lower bound, that's sort of an obstacle. So one of the tools available to us is the Feynman-Koch formula, which I believe if you show that the Feynman-Koch formula is bounded, that's kind of the main thing you have to show. So there's some results that are from Hu, Yaozhong Hu, and DeLang, Carl DeLang, and Carl Mueller maybe that are about proving that the Feynman-Koch formula is bounded on Rn, and it's pretty straightforward to prove it in our case because we're dealing with the compact surface. You sort of just mollify the formula, and then you show that that it converges, and so it's pretty straightforward to show it. So this is the formula that comes from Feynman-Koch, that you have the exponent of the integral. If we put a Brownian motion in for the noise, that is going to give us the heat equation in this situation. And our idea was that this time average is going to converge to T times the space average. And so this is going to integrate to rho for positive rho. So we can't get to rho equals 0 quite yet. This is how we proceeded to make the proof. We just sort of evaluated these integrals. That this is the exponent of f alpha rho bs minus bs tilde ds. It's we get to move the expectation inside from Jensen's inequality. And then we can use you can compare a difference of Brownian motions to a single Brownian motion with twice the speed. And that's related to the properties of Gaussians, that you add Gaussians and get Gaussians. So f alpha rho of B2S. Now this is how we can evaluate it in terms of the definition of this in the Fourier mode as represented with these Fourier bases. Then we want to integrate it, right? We want to evaluate this integral here, and this is kind of like the definition of the Fourier product, right? We're integrating a function times this Gaussian here, and this Gaussian has its own Fourier integral. So the Gaussian integrates to another Gaussian. That's one of the nice properties. So this becomes the product of the nth Fourier coefficient times e to the negative Sn squared. Yeah, this is the probability density for the Brownian motion. And then if we integrate this function e to the in dot times the probability density, that's going to give you the expectation value, right? But in fact, this is a Fourier transform, basically. So it's the nth coefficient. And we have a formula for that. Yes. Um, so e to the in x times the Gaussian, right? This is going to be the Fourier. Why is it not just this Fourier transform? That's it. Yeah, that could be a part of it. Yeah. So then it's going to be e to the 2 inx. This comes in here. Yeah, that's a good point. I have to look at that. Let me think about it a little bit. Yeah, that could give you the correct behavior there. Oh, you know what it is? It's that the Gaussian is not its own Fourier transform. You invert something there. That this comes out because if you take the Fourier transform of a Gaussian, then it's gonna kind of flip things around. This is the inverse. I double checked this a few times a little while ago because the most recent research is not on this Feynman thing. But I think it's because when you take the Fourier transform of a Gaussian, you get 1 over the whatever the width, 1 over the variance rather than the original variance. So then this, once we have that formula, this goes through this way, and you can take the you can produce a convergent series for this here, which is going to be this is, if we look here, we showed that it's greater than or equal to the exponent of this thing. And now we're showing that this thing is going to be rho t plus this part. This part is what's here. So now we showed that it's the lower bound is the exponent ct plus something with the order of a constant. So if you have the case of Rn, you have a critical dimension when there's a transition. And in the case of the torus, in the compact case, there is not really a transition like that. And it's on all dimensions, you're going to have this lower exponential lower bound of growth moments. Yes, there's a slight typo here, which is this one is missing. I think non-zero rho. It depends on non-zero rho. Yeah. F out to make F a positive definite form. We just to make this correlation greater than or equal to 0, and that's why we chose it originally. But that was for the upper bound that we wanted to, because the idea is that this correlation has a lower bound. So when we're calculating the existence and uniqueness, we wanted to move it up a little bit. But in the situation that it's you're doing the now we're doing the lower bounds on the noise. Uh, we don't. It doesn't help you to move the noise up a little bit. You have to deal with the row that you're dealt. So the only issue is that if it's non-zero. And so the future work is my academic brother is named Hong Yi Chen, and he is working on this noise on manifolds because it's written in terms of this eigenvector basis, and so you can write the eigenvectors of Laplacian on different types of manifolds. So he's working on that right now. That's his thesis work. My future work is to look at, as you suggested, to solve for an equation for the solution rather than just having the solution. I think also looking at the intermittency as rho equals 0 is another good thing to look at. Okay, thank you very much, my collaborators. Happy birthday, Volker, and thank you to Miguel and the organizers for your invitation. Uh, like right here in this one here. So time, yeah. Yeah, this is from
You take the paper.
yeah, so this is the definition of the intermittency. Here, right? So it's if you take the exponent, so multiply t times, so t times mp, and then take the exponent. So e to the t mp should be is going to give you the exponent. It's going to give you the pth moment. And I think from the probability perspective, the idea is that um, having really big moment, like so the average is kind of like the first moment, right? And then the second moment is kind of like the variance. If you think about like a bell curve, it's kind of how wide is the bell curve. And then if you take these higher and higher moments, the idea is it's kind of making the tails of your distribution bigger and bigger. Uh, and so then the question is that's kind of the perspective that was used to describe this idea. And now to develop an analytic perspective on it is what are the derivative? So the derivatives are definitely not going to exist on this very rough surface. But I think that's actually a really great suggestion. Yeah. So this is that we want to integrate n to the negative 2 alpha minus 2. So that is going to be finite if 2 alpha plus 2 is greater than d. And so that sum of that subharmonic series is going to be the constant. Yes. Yes, alpha and d. And does this rho t enter it? No, yeah, I think that 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 this intermittency work is ongoing. There could be a lot of improvement to try to understand what intermittency means.
Okay, any other question or remark? No, just a short one. You in one slide you mentioned Brownian bridge,
Yes.
and where does it used? I did not get. I mean, the chance to see exactly where. I mean, it's fine Brownian motion, all of it, and suddenly there is Brownian bridge. What it is used?
So the idea is that this where's the as you continue these Picard iterations, each
Mm.
Picard iteration gives you more Gaussians underneath the integral. And the idea is that when we add a new Gaussian to the old Gaussian,
Mm-hmm.
then you've sort of taken this I guess but if you had you can imagine here there's at first we're going from s to t minus s,
Mm-hmm.
and we're going from x0 to z, then we're going from z to x. So
Mm-hmm.
then if we apply this iteration again, now there's going to be 3 Gaussians
But
under there, right? And it's sort of like each step of the Picard iterations, you're kind of dividing this stochastic process of
but
take the Gaussian, take one step. So it's sort of like, okay, if you run this equation for 1 second, uh, right, with this noise underneath.
but is it not Brownian bridge? Is not a Brownian motion which start at at some point and finish at the same point? I-
Brownian bridge
Bridge
is
is
starting
is
at
it not like not that Brownian bridge?
the Brownian bridge as we define it. I mean, if you want to look at it simply, it's if you this is the probability density of the Brownian bridge this year.
Oh,
Adding a new Picard iteration adds 2 new
so
Gaussians, and
it's not the same definition that I have, so to say.
no, you use a different endpoint and starting point. But the idea is there's 2 pinned. Oh, I get okay. Maybe the Brownian bridge has the same ending and starting point, and this is a pinned Brownian motion. So
Mhm.
a pinned Brownian motion could have a different endpoint and starting point. But the idea is that in the middle, uh, 2 of these heat kernels add up and they become a Brownian motion because this is the density.
I see. Yeah. Okay. Okay. Any other remark or comment? If not, let's thank. Thank you. And we start at 12:30, so we have in I don't know 5 minutes, something like that. Yeah, I thought that Ronin Bridge was something. I thought that Ronin Bridge was something with.